Hello, Dr. Manas.
Hi.
Yeah, hi. Yeah, Sangmitra, you may start now.
A passionate researcher interested in developing codes and methods to model light matter interaction of hybrid systems. He who works on improving and accelerating quantum embedding techniques for molecular and periodic systems. Dr. Manas Sharma, he did his MSc and BSc under University of Delhi. He did his Ph.D. in physics from Friedrich Schiller University, Jena, on the topic density functional theory based embedding for molecular and periodic systems. He is also interested in deep learning and have created a performant neural network library. Apart from this, he is also lively in YouTube tutorials, blogs, and so many. So we have a great speaker in front of us. So participants make use of this opportunity to the fullest. I welcome you, sir, once again.
Thanks for the warm introduction. And okay, so I hope everyone has either installed Quantum Espresso or BORAI, and now we will try to calculate the cohesive energy of the silicon crystal, and we will try to compare our result to the experimental value of 4.63 electron volts per atom that is reported in this publication from 1982. So you can see how old DFT is, that back since 1982, people have been doing DFT simulations, and even probably before that as well. So yeah, so we'll try to reproduce this value. And as I already showed you guys, you can download the silicon CIF file from this materials project database here. And also I sent these resources. I'm not sure if everyone has received these resources, but sorry. But essentially, here there are some links for the CIF file that you can download, and the materials project. So let me just go ahead and paste this in the chat right now. Okay, so yeah, so this would be the link for the materials project, where you will download the structure for the silicon crystal. And you can also I will paste the link for this reference paper. And in case you guys don't have access to BORAI, then to make the creation of input files faster, I'll paste this link as well here. So you can download the input files from this link, and you can also, sorry?
Yeah, now your screen is visible.
Okay. Okay, so yeah, so these are some useful links from where you can download the CIF file, the input-output files in case you don't have BORAI, and then the reference value will be from this paper. And so I already showed in the presentation the formula for the cohesive energy is here. So the first calculation that we'll be doing is, we already did it already actually. So we'll be calculating the energy of the bulk silicon crystal. So let me just go ahead and open this and check the result. So we did it for 8 by 8 by 8 K points with 50 Rydbergs cutoff and 400 charge cutoff, and the resulting energy. What I'm going to do is I'm going to copy this resulting energy and come to Wolfram, let's say, and paste it here and divide it by 8, because I need the from this formula, you can see I need the bulk energy per atom, and there are 8 atoms in my crystal, as you can see from the input file. So there are 8 atoms here, so I'll divide it by 8. Okay, so now I have just as I already mentioned, that quantum espresso already assumes periodic boundary conditions. So it has already assumed that this atom will be repeated along all the three XYZ directions. But this is not what you want. You want the energy of the isolated silicon atom. It cannot be interacting with its periodic images. And to ensure that it doesn't interact with its periodic images, what you can do is you can specify a large vacuum along the three directions. So let me just go ahead and increase the lattice parameter to like 15 angstroms. And now this would be sufficiently separated from all the periodic images. The periodic images will still be there, but just separated from those. And I think there's a question. Something. Yeah, okay. So some people are reporting that BURAI is not working that I expected, that in Linux and some machines it doesn't work. So in that case, what you can do is you can, so if you download this input files from this link, if you download the input files, so you will, are there, so is there, yeah, okay, if someone has raised their hand, please unmute yourself and ask the question.
Hello, sir. This is Dr. Prajakta Joge from Parul University. Actually, my question is that can we be able to understand the polymeric chains arrangement? I mean, how the polymer chains are linked together. Of suppose we are producing some blends, right? So, and moreover, we are adding some salts also. So the ions are the ions are created, and these ions will get bonded with the polymeric chains. So suppose if I want to, and moreover, we can add the nanofillers also. Like it is my work of one of my students. So I wanted to just ask you whether we can be able to understand the chain alignment, the chain arrangement, and the linkages with the atoms and other nanoparticles which are present therein. So, and moreover, the plus size is also there, for example. Then I just wanted to know how Burai is going to help us in understanding these arrangements.
Yeah, unfortunately, so the problem that you're describing, I think it is usually tackled with molecular dynamics rather than DFT. I'm not sure if it is done with DFT as well, but yeah, usually it's done with molecular dynamics, and BURI does have this MD interface, but as I mentioned, I'm not familiar with molecular dynamics. I'm more familiar with, and I think for your problem, it would be best to use Material Studio, which is a paid software.
Okay.
But when I was doing my PhD, other students were working on similar stuff related to polymers and these salts and stuff. So they always used Material Studio. So I would recommend that you can try that. But sorry, I'm afraid I don't have an exact answer for that.
Okay, sir. But in that case, can we have just a trial error method? Like, for example, if I have got a material and if I have got a data for it, can I put it in the software and then I can check or something which I can, just kind of a trial purpose. So can I do that? If you suggest.
I'm not sure. Sorry. Yeah. I'm not sure
It's okay,
about
sir.
that.
Doesn't matter. So it's okay. Thank you so much. Thank you, sir.
No problem. Yeah, so for those who don't are not able to use BURAI, they can just go ahead and download this zip file from here. So let's why is it taking so long? Okay. But anyways, I have this file downloaded actually, so let me just show you. So here you will have this SI conventional and SI isolated directory. So you will directory, and then this would be your input file, this would be your pseudo potential, this is the output file that I already provided, but you will run it by yourself. So I hope you at least install Quantum Espresso. So then what you can do is you can open this with a text editor, and
Hello, sir.
yeah.
Sir, I am trying to run input file in Brave, but I am getting error.
What does, can you show me the screen?
Sir, I am joined in this meeting on my mobile phone, but I am running this laptop, Braille laptop.
No. But like, so if you go to BRAI, then you go to results, then at some point you will see something like so you will, maybe in the log file, if you open and go to the end, you will see some sort of error that you can mention. What error that is?
Yes, sir. Sir, error is showing that it's tag not found.
What's not found?
Tag not found.
Did you come to this SCF tab and then run the calculation, or did you try to run it from the geometry tab itself? Because I think if you'd run it from geometry,
from geometry, sir. From geometry,
yeah,
sir.
so yeah, so you should come to SCF, because then you only these parameters will be specified.
I come to SCF. Now I'm again going to run.
Mhm.
So again it is showing error, and now in result it is showing crash.
Yeah, but can you open the either the crash file or the log SCF file and tell me
Yes,
what
log
does
SCF
it?
file I opened.
Mhm.
Sorry, I opened log SCF file.
Sorry.
Sir, I opened the log SCF file.
So what does the error say? Like at the end, there might be some error.
It's writing application aborted, adopting MPI com warrant error 1 com rank 0.
This is in which file?
Sir, sir, log.scf.
And what does the crash file say?
Sir, crash, sir. So it again says that tag not found.
I'm not sure. So maybe I'll come back to you. Sorry?
Error in IOTK scan begin.
Error in?
Error in IOTK scan begin.
Sorry, I'm not able to understand, but let's, you can keep it on hold, but at least observe what I do in the remaining stuff, because otherwise it will take a lot of time. And maybe you can make a comment on my YouTube channel, or write to me an email or something, then we can figure it out later. But for now, let's move on slightly. And if I have a time at the end, I'll come back to you. And so there's a question, why are we setting occupations fixed? Because we have an insulator and semiconductor. For insulators and semiconductors, the occupation should be fixed. Smearing is used because in metals, the valence and the conduction bands are overlapping, so that you face some convergence problems, because electron can occupy any of the multiple states that they are available. So in order to make the convergence possible, you specify smearing to separate these, but for insulators and semiconductors, you don't need to employ smearing, so you can just set it to fixed. And then how to turn on spin orbit coupling. So that is a good question. I myself have forgotten it, but I think there was something like L spin orb. Yeah, okay. So there is this option L spin orb. Where did it go? Yeah, you can use this to turn on spin orbit coupling. But okay, so coming back to the tutorial. So yeah, so for the isolated atoms energy, so I created a large supercell with 15 angstroms of lattice parameters. Now, what this means is this silicon atom won't be able to interact with so far periodic images. So the periodic image would be 15 angstroms apart. So and also I will have to make sure that I use the same pseudo potential for this calculation as well. So previously the pseudo potential that I used was so the pseudo potential was PBE NL pos. So we should always be consistent when doing these relative energy calculations. We should always use the same settings. So NL pos, I will select that. Go to the SDF tab again. And again, I will use the same values for the cutoff energies. 400. This kind of number of k points doesn't matter because you have such a large unit set, and the number of k points is, or like the distance between the k points is inversely proportional, or rather the reciprocal lattice parameters are inversely proportional to your direct space lattice parameters, so they would be really small. So you can just use a single k point, and again you can use fixed occupations. Save this, let's say by the name SI atom isolated, and then you can run your calculation. Okay. So yeah, while it is running, let me come back and see if there are any questions. Yeah, so okay. And yeah, so yeah, so I was talking about how to do it in Quantum Espresso. So yeah, so you can open if you download these files, then you can open them in a text. I'm not sure why is it not working. Okay, just hold on a second. So you can. Yeah, so you go to these files that you downloaded, go to the SI conventional directory. Conventional directory, and now you see that these are the files that you downloaded. You can ignore these identifier files. They are just artifacts of me using Linux. Like I copied this from my Windows to Linux, so these are just artifacts, these identifier files. But essentially you have these three files, right? And you want to run this espresso.scf.in file. So what you will do is, if you have Quantum Espresso installed, you can check that by doing pw.x, and I get a path for pw.x. So that means I have it installed. In your case, if you compile it manually, you perhaps have a longer path for pw.x that you will have to specify manually. But anyways, I can do pw.x. Then I can say this means that I'm specifying the name of the input file, espresso.scf.in, and then you can essentially hit enter. Okay. Yeah, okay, so it says that the pseudo potential was not found, and that is actually because if you open this input file, sorry, hopefully it opens now. Yeah, so this is my input file, but the pseudo directory is from what I used in my tutorials, but now we have to put a dot here because I have provided the pseudo potential in the same directory that you downloaded. So now you will just replace it with a dot, and you will now try Okay, so this calculation is heavy for my system. It is slowing it down. Okay. There has been an kind of an issue with this calculation actually. Okay, let me see the parameters that I used previously in the files that I provided. Sorry, yeah. Okay, yeah. So the biggest thing I completely messed up. Okay. So the most important thing when running, so let me just go ahead and quit this simulation. So yeah, so that is because I was getting distracted so many times by questions and everything. So yeah, of course, I forgot the most important thing. Okay, so for an isolated atom calculation, it is not so simple that you just create a large vacuum in all the three directions and you just go ahead and run it. It's not as simple as that. You have to keep in mind that this atom has valence electrons or the electronic configuration. You have to keep that in mind and find out how many unpaired electrons do you have. So that is the most important thing. So if you come here and you see that the electronic configuration that I've already written down is 3p2. So there will be 2 unpaired electrons for my silicon atom. So so it's not so if I run the calculation as I did right now, that assumed that each orbital was being occupied by 2 up and down spin electrons, but that is not the case. The last 2 orbitals should be occupied by both up spin electrons. So for this thing, so this is really crucial. So whenever you're doing isolated atom calculations, you have to keep in mind the electronic configuration. So for that, you will come to this magnetization tab, select a collinear calculation, select the fixing method to be atomic. And then for the magnetization, you will just select any starting magnetization value, like an initial guess 0.1. And then if you open your input file, then you will notice that it has these options, n spin 2. So this means you are doing a spin polarized calculation because you now don't have equally paired electrons, but you have unpaired electrons. So you will do n spin 2, and then you specify just a starting magnetization value of 0.1. It doesn't matter. Quantum Espresso will figure out the correct value by itself. And now you should run the calculation. So yeah, so that was, so let me just save it. So that was a big mistake. So sorry about that. And now if you run the calculation, okay. Yeah, okay, so now I'm getting an error, and that is because since I have turned on this magnetization thing, spin polarization, now I cannot use this fixed occupations. Now I am forced to use smearing. Earlier it was optional, but now I'm forced to use smearing, and now I'll have to run it again. Okay. So, okay, so now it is running, and yeah, sorry about that. So yeah, so that is the most important thing whenever you are doing a isolated atom calculation. Always keep in mind the electronic configuration and whether the number of electrons would be paired or unpaired. So yeah. Okay, yeah, so there is a question, what do all these terms mean? So yeah, so even I am not, because I haven't been working with Quantum Espresso since quite some time, but I think I remember some of the terms, but you can also find their meanings here. So this RRKJUS, for example, this means, this US means you're using an ultra soft potential. RRKJ were the authors that came up with it. And then here, N refers to the fact that I think it uses nonlinear core corrections or something like that. And yeah, so here you have an L, which again could either refer to non-local or non-linear core corrections. Yeah, and when you have, I think, this SPN, I think that could mean that you have a fully relativistic, or I mean, you can always ask ChatGPT. I think it may have the answer, but yeah, so there are these terms. So KJ-PAW means that KJ is the author, and then PAW was the projected augmented wave method, and PB is the functional. And I think it's for non-relativist, sorry, a nonlinear core correction, I think. But yeah, it's a good question. And also then you can have non-conserving zero potential. So here you don't have US, so that means that it is norm conserving zero potential. But yeah, it's a good question, and perhaps one can find these meanings in the by googling them. Yeah. So yeah, and whatever zero potential you use, I guess it is best to go through literature and see what people are using these days, and that way. Okay, so the SCF for the isolated atom has also converged. So now I will pick up the isolated atom's energy, copy this, come back here where I pasted the total system's energy, and then subtract the isolated energy from that. And yeah. Are you able to hear me? Because I think my internet is not working now. Or
Yes, sir, you are audible.
Yeah, it is audible.
okay. Okay, cool. So I get this value in Rydberg, so I can go ahead and copy it. Copy it. And this, I have this web app where, so at this URL, I have this web app where we can go to this unit conversion thing and specify the input unit to be Rydbergs, paste the value, and we get this value minus 4.51 Rydbergs. So as I mentioned, so the formula that I showed, I had this negative sign here. So it's all based on convention. If you have your conventions clear, then it's you can ignore this negative sign. So right now, this convention, this formula that I have of bulk per atom minus isolated atom, this means a negative value will, if I ignore this negative sign outside. So if I ignore this negative sign outside, then I will get a negative value, which would mean that the cohesive energy is like the system is stable. But since I was comparing to this paper where they used positive values, they used a convention of positive values. So that is why I put that negative sign in front to match their convention, where a positive value indicates that the crystal is stable. So compared to their 4.63 electron volts value, I'm getting 4.51, which is okay because there are a lot of approximations that we have used, and also the results may depend on the zero potential, exchange correlation functional, and also the lattice parameter. So they used a parameter of 5.429, while we just downloaded the file from materials project, and there the parameter was 5.44 compared to 5.43. So there's a very small difference. But yeah, so due to the zero potentials, exchange correlation functionals, so it's somewhat reasonable. So we get an error of 0.1 electron volts per atom. So has anybody else been able to do this calculation? Yeah, so usually usually these NL zero potentials I have found to be all right for my calculation. So NL and the KJ-PAW zero potentials, or NKJ-PAW, and spin, I'm forgetting. I think I'll have to, maybe I can Google quantum espresso zero potential explained. SPN was for full relativistic or what? Okay, so rel is for full relativistic. Then, okay, so this is for NL. Okay, so SPN means, okay, so SP basically means that you have semi-core state, some like S valence semi-core state, and then P valence semi-core states, and N is for non-linear core correction. So if you have like SPN, that means you have S and P semi-core states in valence and non-linear core correction. But I mean, the best is to always try to find out what people are using in literature, and then also do your calculations and see which pseudo potential results in the best estimate for the property that you're investigating. So it's usually good to do calculations with like 3-4 pseudo potentials and find it out, which would be nice. And could you please explain again the concept of unpaired system in the case? Yeah, so essentially it's not related to just cohesive energy, but anytime you are doing like an atomic calculation with quantum espresso, so your atom, so by default, quantum espresso assumes that each orbital would be occupied by both up and down spin electrons. But in case of an atom, you have to obey this, or this Hund's rule and Aufbau principle. So if the electronic configuration for the valence electrons is 3s2, 3p2, so S would be occupied completely by up and down spin. But for 3p2, you start by occupying. So the up spin orbital start filling. So you have the first up spin orbital fills the first p orbital, then the second p orbital, and then if you had more electrons, then they would have been filled, and so on, and then they would have been doubled. But since you only have two p electrons, so you have both of them with the up spin. So that is why your calculation should be, so you have unpaired electrons. So that is the moral of the story. So whenever you have unpaired electrons, you should employ n spin equals 2 and provide a random starting magnetization. And also, let me show you an interesting thing. No, n spin 2 doesn't mean that it has 2 unpaired electrons. It just means if n spin is 1, then that means what we were doing till now. So that was by default. And n spin 2 simply means that it is a spin polarized calculation. It doesn't have anything to do with the number of unpaired electrons. And interesting thing that I will show you is in the output of this isolated atoms calculation, you will, at each SCF iteration, now you will have a magnetic moment, and that would be actually 2 Bohr magneton per cell, because you have 2 unpaired electrons. So you can see iteration, yeah, total magnetization. So now you see that at each iteration you have this. So quantum espresso by itself, even though you provided a starting magnetization of 0.1, by itself it found that the total magnetization for this cell is 2 Bohr magnetons per cell, because for each electron you have 1 Bohr magneton magnetization. So you have 2 unpaired electrons, so 2 Bohr magnetons per cell, and that is how you can be sure that your calculation is employing the correct electronic configuration of SI. So this also you should always check. Yeah, so this is also something you should check. And yeah, so I hope some of you were able to get this result of like 4.5, 4.6 electron volts. And then we can move on to the absorption energy calculation. But can someone tell me if they completed this cohesive energy calculation somehow? Or I guess I can wait 7 or 8 minutes until 12:20, and you can try to run this. So you essentially do calculate the energy of the silicon bulk crystal with 8 atoms, divide that by the number of atoms, you get the bulk energy per atom, and then subtract the isolated atoms energy. You get the value in Rydbergs. You have to convert it into electron volts. And I think one Rydberg is 13.6 electron volts, or 13.6 electron volts. So you can yourself also just convert it here by multiplying by 13.6. Yeah, so 4.51 electron volts. Yeah. And also for the spin orbit calculations, and someone asked this. So for spin orbit calculations, I think you will also have to use this this thing. So this polarization, instead of collinear, I think it would be non-collinear. Yeah. So when I do it, it already asks me about spin orbit. I'll say yes. Yeah, and now if I reload my input file, it says non-collinear true and L spin orb true. And what else? Yeah, so these are the two changes. So that way you can do spin orbital coupling, but you can also have perhaps you'll need to use a different, like a fully relativistic pseudo potential for this. So in this, for spin orbit coupling, you will have to use a pseudo potential that has this rel keyword, I think. Yeah. Yeah, so the spin orbit coupling here. Hi, yeah, so I'm facing some power cuts, so the Wi-Fi got restarted. Okay. Unfortunately, I have lost the previous messages, so I'm not sure if there were any questions there. Okay. And I see that someone has raised their hand, so please unmute and ask.
Sir, can you please quickly repeat how you calculated the cohesive energy? Uh,
So yeah, so you just calculate the energy of your total silicon crystal. So you get something like minus 373 if you use the KJ PAW pseudo potentials that I mentioned. So the energy will depend on the kind of pseudo potential you use. You want to get the same energy. But yeah, so you will get something like this, and you will divide it by the number of atoms in your silicon crystal. So this quantity would then be the bulk energy per atom. And then you will subtract the isolated atom's energy. So this way and then you will get a value in Rydberg. So you will convert it into electron volts by multiplying with 13.6 electron volts. And regarding this question, please brief the method to calculate cohesive energy, like in which format and how to download. I'm not sure if I understand correctly. Basically, you just open materials project, you click on this link and download the zip file from here. So you get the crystal file, and then the isolated atoms file you can create by yourself. For example, I just imported this CIF and deleted all the atoms and modified it manually, but you can create it by yourself because it doesn't need to have any crystallographic information. It's just an isolated atom. I'm not sure what you mean here. There are 8 atoms. I'm not sure for what do you mean 8 electrons? Do you mean this number here? So this is because the unit cell has, let me open it again. So unit cell has 8 non-equivalent atoms. So for example, if you select this corner atom, then that means only in my input I only specified an atom at the origin, but the remaining corners were just filled, or like it's just showing you by symmetry by repeating due to the periodic boundary conditions. So they are not really what you specified, but rather just by symmetry. So yeah, so when you will have at the corner, then you have on the face you have 1, 2, 3, 4, 5, 6 faces, right? So you have 6 atoms on the faces. Each atom contributes half to your main cell. So you have 3 atoms on your faces. So you have 4 atoms now, and then the remaining are inside, not on the face, not on the edge, not on the corner. So you have this 1, this 2, and this 3, and this 4. These you have inside your cell. So 4 inside, 1 at the corner, and 3 on the faces. So that's why you have 8 atoms. Because yeah, so the other atoms were just generated by symmetry. I provided 8, and then BURAI just decided to, so that it looks nice compared to what you see in books. Otherwise, some software don't really visualize it like this, but rather, let me show you. So in this app that I created, I can just enter this MP149, right? So so for example, here in this visualization, let me switch to conventional. Yeah, in this visualization, this doesn't show you the equivalent atoms that were generated by symmetry. So that just depends on different programs use different ways. For example, Vesta decides to just you even display the atoms that are outside the boundaries. So this is another way to visualize. So every software has a different way of visualizing, but you should have your concepts clear. From where you have written isolated energy, and total energy means where it is displayed. Okay, so it's if you go to the output result, then your output, then somewhere if you search for like the exclamation mark, then at some location you will have this. So at the end, right below where it states highest occupied stuff, so it will have total energy with this exclamation mark. So you can find it that way. So from here, you will get the total energy. Okay, so and isolate, I mean, it's just the same. So even for isolated, you just open the output file, and so nothing changes. So you just open the output file. Again, you go to the end. Yeah, here. So again, you have this. So this time, instead of the highest occupied thing, is this time it reports the Fermi energy, because we use smearing. In case of smearing, it reports the Fermi energy rather than the highest occupied. And also this time, you can see that for each K, I mean, we only have the gamma point, but for this K point, it reports the orbital energies of the upspin electrons as well as the downspin electrons. So this time it is a spin polarized calculation, unlike before. Okay, so I guess this is time to move on to the next calculation for the adsorption energy. And for this, we will be referring to this paper that came out in 2017. And they studied the adsorption of water molecule on the LiH001 surface. And here is the structure for that. And we will try to reproduce this value reported here. So here they report that when they have 32 atoms in the substrate, that is the surface, then they get a value with the PBE exchange. So PBE is a very popular GGA type exchange correlation functional, which I already mentioned. So they get a value of 219 milli electron volts, actually, milli electron volts, with just a gamma point. Now, whenever you are going through papers, always try to see if they have provided the structure that they used in the supplemental material. In this case, we are fortunate that they did provide this structure in the supplemental material. However, they did so in a PDF format, which is not very convenient for your calculations. So, but yeah, so here they have the structure for the H2Li8H8. So this has 16 atoms in the substrate, and this has 32 atoms in the substrate because it is Li16H16. And we want to reproduce, as I mentioned, this one, because they haven't reported the result of the 16 atom substrate. So we want to reproduce this 219. So we will go ahead and copy this structure. And this is actually in the WASP postcard format. So postcard format is used by WASP. So I copy this, and then I go to this app, rippertools.turbomole.org, that I created. And let me just put this in the chat again. Chat. There is a question: if I have bulk material of 3 atoms, then then you will divide the bulk energy by 3 and then subtract the isolated atoms energy. So that would be if you have 3 atoms. Yeah. Okay, so I pasted this link in the chat, and you can just go ahead here, go to convert other formats to Ripper. select the file format to be postcard because that is how they provided their structure in this supplemental information. Then you can paste the contents here. So you can see that all of this is here, and then click anywhere outside this dialog box, and you get that the structure has been parsed. And now what you can do is you can just download this zip file. So I download this zip file and I open BURAI, and then I import this zip file back in BURAI like this. Okay, so this is the structure. So we have this. So as I mentioned, so now we have a 2D system, right? So because we are studying absorption of a molecule on a surface, we don't want periodicity along the third direction. But since quantum espresso inherently has these periodic boundary conditions, so we provided this vacuum along the third direction, that is the z-axis, and after that it replicates the atoms. But this is probably enough to make sure that the periodic images are not interacting with each other. So yeah, so now in order to calculate the absorption energy for the system or for the water molecule on the LIH surface, we will follow this formula. And yeah, so the formula is that we need to calculate the energy of the total system with the adsorbate as well as the surface. And this is my total system right here. So I'll again, check what pseudo potentials are being used. And right now I see that all of these are of different types. So this is a Vanderbilt non-conserving pseudo potential. This is an ultra soft pseudo potential, and this I don't even know. So let me make sure that all of this is consistent. So I'll perhaps use this SL KJ POS pseudo potential for Li. For H, I will use this KJ POS, and for O, I will use this NL KJ POS pseudo potential. And then I will go to the SCF tab. And before I do that, actually, I'll come back to the geometry tab and see what is the recommended wave function cutoff. So that is around 50. So I'll just go ahead and open SCF tab, put in 50 here, and just use a value like 8 times of that. Although you could have also used a lower value to make it faster. And the number of K points we'll just keep 1 because we are trying to reproduce the gamma point result. And again, occupations would be fixed because this is sort of an semiconductor or an insulator. And now you can go ahead and save it. Let's say by total LIH plus water. So this would be the name for this project. And then I can go ahead and run this. Okay, so this is running right now. And so, yeah, so right now I'm running this calculation. E adsorbate plus surface, and then I will calculate the energy of just the surface and then just the adsorbate, that is the water molecule. And in the meantime, let me check if there are any questions. Yeah, no. So yeah, so while this calculation is running, let me go ahead and create those files for just the surface and just the molecule. So first, I'll open this CIF file again. So I'll go to the recently used and then open this CIF of the total system again. And for just the LIH, I will just simply go ahead and delete these atoms corresponding to the water molecule. Okay, and now I will save this as surface LIH, save. And again, I will make sure that I'm using the same pseudo potentials because that is really important. For Li, I used SL KJ previously, and for H, I used this KJ. Okay, so now I will go ahead and save it again. Go to the SCF tab, use the same cutoff as before, 50, 400, and occupations fixed. and I'll go ahead and run it. And this will make BURAI put this calculation in a queue. So once the previous calculation is completed, it will automatically start this surface calculation. And now what I will do is I will create another project from the same zip file. And this time I will delete all the LiH atoms and just keep the H2O atoms. So I will open the input file and go ahead and delete all these atoms except the last three that correspond to the water molecule. And then I will press this up arrow here, and this will make the changes reflect in the GUI. However, this time you will see that we have just an isolated molecule. So while the vacuum in the Z direction may be enough to separate it from its images, the vacuum along the Y and X directions is not really enough to separate the periodic images from interacting with themselves. So for that reason, I will, what I'm going to do is I'm going to, let's say, select cubic cell and just make the lattice parameter to like 15 angstroms. And this would be better. And also to make the visualization slightly better, let me go ahead and put this at the center somewhat. So yeah, here it's nice and centered. Yeah, so this looks nice. Okay. Yeah, so this, I mean, centering it doesn't have any effect on your results. So I just do it to make the visualization look much cleaner. So now I will again specify the zero potentials to be the same as before. So KJ and sorry, not this one, this one. Yeah. And again, I will come to the SCF tab, specify this to be 50, 400, fixed, and save it. Let's say isolated water. And run this as well. Okay. So the first calculation on the total system has actually finished. So let me go ahead and check the energy. So here is the energy of the total system. Let me go ahead and copy it. Okay. Come to Wolfram and paste it, because the first energy, as you can see in this formula, we needed for the total system. So I pasted that, and then I put a negative sign to subtract the energy of the isolated systems, and they will come in parentheses once I have them. So I'm waiting for those to complete. So yeah, these are still running. Okay, so the surface isolated surface LiH is also complete. So let me go ahead and search for the total energy. Copy it, paste it in the formula I have here, and then just wait for the last energy. Okay, so there is one more question, but I'll just come to it because I think it's I'm going to be getting the result soon, and let's not break the continuity, otherwise it gets confusing. So let me just wait for this to complete. Okay, so this is also complete. Paste it. So this is the absorption energy that I get in Rydberg's. And now to get it in electron volts, I'll multiply it by 13.6. Sorry, I had to multiply the whole thing, not just the last number, sorry. Yeah, so now I get it 221, so like 0.221, so that would be 221 milli electron volts. And my convention, as I already mentioned in my convention that I'm using here, negative value, because whenever you have the total energy value up front, and then the components or the constituents energy, then always a negative value indicates that it is stable, while if you use a reverse formula, then where you have the constituent energy up front and then you subtract the total energy from it, then a positive value indicates that it is stable. But in my convention, a negative value indicates that it is stable, so or the adsorption is feasible. So this is what I'm getting, 221 milli electron volts compared to 219 milli electron volts, which is really close. And since they are getting a positive value, they probably use the reverse convention, as you can perhaps see. Let me see here. So yeah, as you can see, they use the reverse convention. So they put the energy of the total system later on, while upfront they use the energy of the constituents and then subtracted the total system energy. So that is the reason for the different convention. Now coming to this question, so how you make this system for calculating the absorption energy. So I didn't really make this system. I just used the information in the supplementary material. And when I opened it, since I'm very familiar with WASP, I immediately noticed that these are in postcard format, but even it is mentioned here that these are in postcard format for WASP calculations. And this is the reason during my lecture, I told you about so many libraries like PyMatGen, ASE, Vesta, so that you can get familiar on how many formats that exist and how you can, convert from one format to another for your purposes. So as I know, my BURAI software likes either CIF files or Quantum Espresso input files or even XYZ files, but it doesn't or maybe I haven't checked, but I don't think it accepts postcard files. Maybe it does. But anyway, so since I noticed that this is in postcard, I just copied these contents and pasted them in this web app that I had created for TurboMole, but it works for this as well. So in this web app, I go to convert other formats to Ripper, select the input source format to be postcard here, and then I just paste the postcard file contents, and then I get this structure here, and then I just download this CIF file, which can then be imported into URAI. So that is what I did. You can also create this structure yourself, but then you will have to do many more calculations, because you have to make sure that you have optimized the geometry. So first you will have to create a slab, LIH slab. You will have, by introducing this vacuum, if you do it manually, by introducing vacuum, you will have to optimize the geometry. Then you will have to place an H2 atom again manually over it at the correct distance, whatever is mentioned in the paper, and then you will still have to optimize the geometry just to be sure. But in this case, I wanted a one-to-one comparison with that paper, so I'm not optimizing or anything. I'm just using the structure that they used. And also for more realistic calculations, like, I mean, here I was comparing to an existing paper, but if you are doing your own paper and you are studying absorption of a molecule on a surface, then you can't just calculate the isolated molecules energy, isolated surface energy like I did. I did that because that is how they did in that paper. You will have to also optimize the geometry of the constituents. So first you create the surface, you optimize the geometry, then you create the molecule, you optimize its individual geometry, then you bring them two together, you optimize the total geometry, and using these three optimized geometries, you will have to calculate the absorption energy. So that is how you would do it realistically, or like in your paper, unless you are comparing to another paper where they also then you can follow whatever they did. But yeah, so yeah, so any questions now?
Hello, sir. Hello.
Yeah.
So I want to ask, like for optimizing the structure, first we need to converse the cell parameter as well as we have to do the BC relax also.
Yeah, so ideally the process goes like this. So you take the LIH bulk cell. So you don't introduce vacuum right now. You just take the LIH conventional unit cell, and then you do VC relax. So then you can get the optimized cell parameters as well as the atomic positions. And now you create a supercell along the X. You extend it along the X and Y axis, while the Z axis you just introduce a vacuum. And
Okay.
now you don't you should not do VC relax, uh,
Mm-hmm.
because ideally what is done is you take these cell parameters from your bulk calculation, and then when you create this slab, you can keep the upper three layers I mean, you can keep the lower, you can freeze the coordinates of the lower layers, while the upper layers that interact with the molecule, you can optimize just their atomic positions. But the cell parameters or the lattice parameters, you keep the same as your bulk LIH. And then you can either optimize all the atoms or just the upper layer. I mean, ideally, you should only optimize the upper layer atoms, because you're trying to simulate a physical picture where you have a bulk surface and you just cut it. But when you cut it, the lower portion of the structure doesn't really change. So that follows the bulk atomic positions, cell parameters, while just the surface atoms, when they come into contact with other environment, they will change. So that is why you just optimize the positions of the upper layers. For water molecule, you don't need to do VC relax, because it's just a molecule. You just need to optimize atomic positions, keeping a large unit cell.
Okay, sir. Thank you, sir. Sir, I have one more question.
Yeah.
I want to ask, like, suppose we are doing a small calculation. So in that case, we can install the Buri in our system and we just proceed with our calculation and we will get the result. Suppose if we have a system which is like we have to make a supercell. So in that case, when we try to calculate the vacancy formation energy of the system in case of bulk system, so in that case, the calculation will take sometime 2 to 3 days. So
Yeah.
suppose if we wanna run the calculation in the Buri, so like so for in that case we are using cluster, right? So can we install Buri in the cluster and we run the calculation in the Buri? Is this
I
possible?
mean, no, as far as I'm aware, you cannot do that, but it's like, as I showed you in my terminal. So like once I have the input file, I just needed to change one line from the BURAI. That is, I just updated the directory where I had the pseudo potential. So you can use the
Okay.
input file created with BURAI, and with very few uh,
Hmm.
changes, you can just simply run it on a cluster by
Okay.
this command. So, and you will, in that case, you will have to do NPI, because on a cluster you want to use many processors. So you will do like NPI run NP4 and put the output to some output file, and like this. So this.
Okay. So overall story is like that. In case of Burai, we can just analyze the structure and we can make the script file, and that script file we can run in the cluster, right?
Yeah. Yeah.
Okay. Thank you,
Exactly.
sir. Thank you so much.
No problem. And yeah, so there's one question: each system should be in the same. I mean, LIH and the LIH plus H2O system should be with the same unit cell, but the H2O molecule cannot be with the same unit cell, because, as I mentioned, that to simulate an isolated molecule, if I use this this cell, then it has enough vacuum along the z direction, but not enough vacuum along the x and y direction. So for isolated water, I actually modified the cell to have a large vacuum along all the three directions. So you cannot really use the same cell for all the systems. But for the surface and the surface plus adsorbate system, you can use the same cell parameters. Why optimization is necessary is another question. So yeah, so I mean, because so whenever you have a bulk material and if you cut it at some place, then it's the atomic geometry along the surface, when it comes into contact with other environment, it changes, because the original structure was when there were more atoms interacting with it, but now you have reduced the number of atoms. Now there might be more freedom to some atoms that they may try to relax. So of course you will need optimization. And similarly for the adsorbate, so this H2 molecule, when isolated, like in a gas, when you have vapor phase water molecules, they may have different bond length or different bond angle compared to when you bring it closer to another surface, where it will now start interacting with it either through hydrogen bonding or like even through other means. So of course you will ideally, if you are trying to reproduce a chemical process, then you will have to do optimizations. And since we are talking about optimizations, let me just go ahead and show you that you have this optimize tab here, where you can tell it whether you want the cell to be relaxed or not. So so the question is, optimization equals to VC relax, right? I mean, optimization means two things. So either you just optimize the atomic positions, keeping the cell parameters fixed, or you optimize the atomic positions as well as the cell parameters. So when you do both, then you say VC relax, otherwise, because that means variable cell. Otherwise, you are just optimizing the positions. For example, here, if I don't have variable cell, at least for the water molecule, there is no meaning of a cell. It's just a molecule. I'm just using a cell because that is how quantum espresso works. But there is no meaning of a cell. So here, there's no point in turning on this variable cell. I can simply just run this and start optimizing the water molecule. However, for the LIH surface, again, yeah, so LIH surface, I mentioned that you should use the same cell parameters as your bulk. But at least for the, let's say, for a conventional unit cell, when you're doing a bulk calculation, then of course you can turn this VC relax on, and because you want to find the like the lowest energy possible with your method. Yeah. So yeah, so if you turn VC relax on, then both the cell parameters and the atomic positions are optimized. Otherwise, only the cell atomic positions are optimized. Yeah. Okay, so we are close to the end of this session. So if you have any questions, you can try to ask them before 1 p.m. I think. What's the time? Yeah, so the lunch break is at 1 p.m. So yeah. So yeah, I mean, the general workflow in BURAI is to get a structure from somewhere, be it a zip file, be it a quantum espresso input file or whatever, and then it automatically gives you this geometry tab. Here you can specify the pseudo potentials, and in case you want to introduce an impurity or doping, then you can use this atoms tab to either delete an atom or replace it by something else, like let's say another element. Then you will go to the SCF tab. You will fill out the cutoff. I mean, you should ideally figure out the cutoff wave function cutoff yourself, but you can also use just really high values like 50, 60, 70 Rydbergs, and then use like a 5 to 10 times value of that for the charge. If the smaller your cell, the more number of K points you need, the denser should be your K grid. The larger your cell, the fewer K points you will need. And for insulator or semiconductor, you just use fixed occupations, otherwise you use smearing. Once you have this SCF calculation done, you can do band structure calculations, density of states calculations, etc. And also, in case you wanted to optimize, then instead of doing SCF first, then you will start with optimize first. So yeah, so somewhat like that. Yes, ideally, you should take the relaxed structure whenever you are doing something like you're trying to mimic a chemical process, and you should use relaxed structures for further calculations. Once you have the optimized structure in VRAI, it is possible you can create you get a button where you can create a new project from those cell parameters. Yeah, cutoff charge you have to specify, and it depends on the kinds of zero potentials. For example, for ultra soft zero potentials, it is recommended. Okay, VASP doesn't have that option. Okay, maybe they figure it out by themselves. But so for ultra soft zero potentials, you use a value that is like 8 to 12 times of your wave function cutoff. While for non-conserving zero potentials, you can use like 4 times, but you will find it online what can be used for different kinds of zero potentials. Whenever you're studying like a realistic, really large system, then you always spend time first figuring out your parameters for the calculation. It takes some time, but don't be impatient and try to go to the bigger system first. Always try to take some time with your small system. For your bulk, let's say LIH or silicon crystal, always try to figure out what is the optimum cutoff, energy cutoff that I can use, because the larger you use, the more time taking your calculation is. Try to find out the minimum value that can give you converged ground state energy, then find out the minimum value that you can use to get the converged cutoff for charge as well. So always try to find out all these, converge all these parameters. Once you have done this, then you can be relaxed that your calculation would be nice. So there's some question on can you show density of states? I don't think there's now much time left for that. Essentially, you just go to this DOS tab and you specify a denser grid for density of states, and then you just run the calculation. And then is there any trick to find cutoff E? I mean, yeah, there's a trick. You have to just plot the convergence, the total energy with respect to the cutoff. So on the x-axis, you will have cutoff, y-axis, you will have total energy, and as it converges, you can see at which point it converges. And then there are 2 questions from 2 participants, so you can please unmute yourself and ask.
Hi, yeah. So can you write down the reference websites or libraries where we can, confirm like the values? For example, you say that we should be doing for smaller molecule first, but we have to confirm it, right? Like whether we are doing it correctly. So if you can write down the libraries for us in the chat box.
I mean, for like crystals, I already suggested this materials project database. So there you can find the band gaps and try to compare.
Can you suggest something for organics like polycyclic aromatic hydrocarbons?
I'm not sure if I know a database where you can get properties, but always you can, for example, in these cases, I refer to papers. So you can always search on Google Scholar a similar paper on the same material, and then you can try to
Okay.
reproduce that.
Okay, thank you.
No problem. And the next question.
Hello.
Yeah.
Yeah, I have one more question. So, I tried to calculate the vibrational frequencies of some molecules. So for bigger molecules, sometimes, I get negative frequencies. So then, I'm like, I searched in the, in Google and in other resources, and then it asks me to change the geometry of the molecule and then try it again. But then it takes, a lot of time because I have to, it's like trial method.
Yeah.
So
Yeah.
do you have a easier way to, address this issue?
No, I also only know this trial and error thing. Like
Okay.
you can distort it slightly.
Haha. Okay. Yeah.
Okay, so I think it's we can end the session now.
Yes, sir. Yes, sir. Yeah.
Thank you so much, sir, for the wonderful sessions. Now I invite Dr. Sanjay Kumar Singh, sir, for delivering the conclusion.
Yeah, thank you, Sangmitra. Thank you so much, Dr. Manas. I'm very happy today through your lecture. I was also learning a lot from your theoretical lectures and hands-on training. I hope participants can be able to find cohesive energy and absorption energy easily. So thank you once again, Dr. Manas, for sparing your valuable time with Chase Foundation. Thanks to participants for joining dedicatedly and asking lots of questions. Once again, thank you. Now I would like to request from all the participants and the speakers kindly on the camera to take a group photo with the speakers.
Manas sir, can you unshare your screen?
Yeah, I request from participants kindly on the camera for a moment so that we can take a screenshot. Kausal sir, I will take a screenshot.
Yes, one second. So I have seen only a 9 people kind of this. I don't know.
Okay, no issue, no issue, sir. No issue. Thank you once again. So now we'll rejoin the session at 2 p.m. There is 1 hour lunch break. So kindly rejoin at before 2 p.m. so that we can start at particular time. Thank you once again. Thank you, Dr. Manas. Thank you, Kaushal sir. Thank you, Sangmitra, for
Thank you.
participating.
Thank you, everyone.
Okay, bye.